Engineering 305, this is Chapter 9, Section 1 and 2 on column failure. The course learning objective for this section is number 24, which is to solve the relationship between the buckling load, material, and column geometry, including the end conditions. And that's not all going to be done in this lecture. The end conditions actually is Section 3, so we won't be doing that, but we will be doing the first one. Buckling load, material, and column geometry. We'll be solving those. I do want you to note, this is objective 24 out of 25. We're almost there. So the equations from the study guide, there are two of them, equation 9.1 and 9.2. They're both in that second section. And they are the critical load is equal to pi squared EI over L squared. And then there's this version, which is really the same equation, but it's given as a different, you can see it a little differently in terms of it's the load over an area of the, and what that interprets to, the reason we do that, even though it's the same equation, is we then can call it a critical stress instead of a critical load. We're used to having things failing at a stress, and so it allows us to talk the same language, even though it's the same as a critical load. It ties back to what we had. So and we've rearranged the equation a little bit. So let's imagine that we take this item, whatever it is, and we push on it from the top, exactly the way that we're illustrating in this photo here. And we put that load on. How does that fail? Well, we go back to chapter 5. We've already solved these problems, right? This is a simple axial load problem. That's correct. That's correct. We get our stress is equal to force over the area. But then what you saw in class 2 weeks ago, Monday, 2 weeks ago, was if it's long and slender like the yardstick, we push on it from the end. In fact, this is what we did on day 1, isn't it? We pushed on it from the end, and then we got this other kind of failure. What happened? It started to flex and bow in the middle a little bit, like this. Well, when we do that, we get that little bit of flex. If I could draw a straight line, and a bigger question you probably have is if you could draw, that would be an improvement. But if I drew that straight line, you can see there's a little deflection there from there to there. That distance is delta. And what happens is as that moves a little bit delta, then that load P is no longer just creating an axial load, but it's creating a moment about this point. I could draw it. There's a moment there, and that moment is equal to, I'm going to call it a minus P delta. Why am I going to call it minus? You're going to see a second. I can change the sign. I can define those things. But do you remember what we just finished up in chapter 7 and 8? Actually, it was chapter 8. That's where we did this part of it. That was equal to EI times the second derivative of delta with respect to x. See that? I know, a lot of calculus, a lot of classic differential equation. So let's move on, we'll attack that. How do I attack that? Well, first thing, let's write down the equation again since it's on the other page. But I'm going to write it a little bit different. Plus, and that's the reason why I put the minus in before, EI P delta equals 0. And I should even probably rewrite that one more time. D squared delta, the second derivative of the deflection with respect to x, plus P over EI delta is equal to 0. Now, you'll remember that I just use that constant, and if you're reading through the textbook, I think they call that just temporarily for solving it. They call it P. Isn't that great? But this was a capital P and that's a lowercase p. I don't want to do that. I don't want to. What you're going to get when you solve it, you got to go back to your differential equation days. And I know some of us are going to struggle with that, but you're going to get that delta is equal to A times cosine P over EI x plus B sine P over EI x. And now that becomes, there was a whole, remember differential equations, whole thing on general solutions, particular solutions. This is our general solution. And now we can start to solve that in light of what did we do in differential equations, and what did we do in chapter 8? We applied boundary conditions to this thing. So let's move forward and start to solve those. So let's rewrite that solution, but do it appropriately, and that is I dropped a square root. It's A cosine square root P over EI x plus B sine square root P over EI x. And now we apply boundary conditions to solve that so that we know what the value of the terms are. So I have two boundary conditions. I have the boundary conditions at either end, right? Which is exactly what we did with the beams. Delta at 0 is equal to 0. And so if delta is 0, well, cosine of 0 is 1. So that's A plus, and sine of 0 is 0. So that's that. So you get out of that statement, A is equal to 0. Cool. Okay, back to next boundary condition. Delta at L is equal to 0 is equal to, well, I already know A is 0, so I'll just get rid of that, is equal to B sine P over E I x. So that is going to be true whenever P over EI x is equal to n pi, where n can be equal to 1, 2, 3, 4. But which one do I care about? Which one do I care about? Which value of n? Well, you can see that P and N are directly proportional to each other. So the lowest load at which I buckle is where N is equal to 1. And then I'm going to get, well, I'll simplify it on the next page. So square root of P over EI x is equal to N pi. Well, x is equal to L. It's not equal to x. It's equal to L. All right. And N was equal to 1. So what we've got is, I'm going to square, I'm going to do it in 2 steps. P over EI L is equal to pi. I don't like the way I wrote that at all. EI and then L, because that's outside the radical, right? Now I want to square both sides because I really don't like this answer. I really don't like the way this is formulated, right? I don't want to deal with a radical. And I've got to get back to P. So it's P over EI L squared is equal to pi squared. Now I can solve for P. And P is equal to pi squared EI over L squared. That is equation 1. And that's when my load is going to cause it to buckle. That's when my load is going to cause it to buckle. Isn't that cool? Great. So we need to do one more shift to get to equation 9.2, and that's to look at the critical stress version of the equation. And so that changes it up, and it helps us define and look at the beams a different way too. We start to look at the slenderness ratio, but we're not going to look at the slenderness ratio until we get to section 6 of this chapter. So we need to do a substitution, but the substitution comes out of geometry stuff, and that is that this section modulus I know capital I, wrong font, whatever, is equal to R. Okay, because pirates, I've been watching Holiday Weekend, I've been watching sailing stuff. It's A times R squared, but of course PowerPoint doesn't do the squared really very easy. So I just put it in pirate terms. R. This and what that is, that's if you think about the units, this is still got in inches to the fourth or meters to the fourth. It's still got the right units, but now I'm going to substitute. So my formula had been P critical is equal to pi squared EI over L squared, right? Now I'm going to substitute ARR in for I. So it's pi squared E. I is equal to AR squared over L squared. And now you can't see it, but you can. And that is, I'm going to rewrite it again, pi squared E A R squared over L squared. And that R squared over L squared is the slenderness ratio, but we write it this way. Pi squared E L over R squared. And then I'm going to leave my area right there for the moment, but you can see I just have to pull it over to here. And then I've got two new things that I developed. This one is the critical stress, so that I can think about this, because a lot of people still want to say it's a stress that causes the failure. Well, is stress a made-up thing? I don't know. Stress, is it? That's the way people want to think about it, so we think about it in terms of a critical stress. We tie that back to the cross-sectional area of the column. And then the other thing that introduces is L over R, which is the slenderness ratio. And you might say, why do I care about the slenderness ratio? Well, the reason is, and we kind of looked at it in class, and we kind of looked at it, if I have something short and stubby, when I push on it, it doesn't fail. It doesn't collapse. I crush it. Remember the cement lab you did freshman year, long time ago? Cement lab, we crushed it by pushing down on that. And it didn't have a column failure, but yet the yardsticks are long and skinny. They have, well, that's related to this concept of the slenderness ratio. That if it's got a small cross section and it's really long, then it's going to buckle. And if it's short and stubby, then it fails with chapter 5 kind of ideas, a force over an area. And we'll see that in section 6 of this chapter. What's next? Example problem 9.1. Example problem 9.1, where we have an 8-foot long pinned end, that's how we derive these equations. A pinned end timber, which has 2x4 cross section, determine slenderness ratio, the buckling load, and the ratio of the axial stress under the action of the buckling load to the elastic strength of the material. Elastic, that's an interesting word for me. I'm going to say that's I would say that's the yield. And when we get really good, we can throw in a different word and they mean the same thing, but it's a different word. And it's kind of what happened here. But we'll do example 9.1 next. I hope you're having a good day. Don't worry, there's more coming.